Today we are going to take a look at the beginning of section 4.2. This is not a terribly long section, but it has some interesting features in it. We're going to take a look at prime numbers and composite numbers and breaking composite numbers down into their primes. So the first thing I'd like to talk about is some definitions of all those words I just said. All right, prime. So a prime number is any positive integer with exactly two distinct positive divisors, namely itself and 1. Composite number is any positive integer with more than two distinct positive divisors. So it automatically has the numbers 1 in itself, but it has more than that. For example, the number 6 has 1 and 6, but it also happens to have 2 and 3. Factorization is any expression of a number in factored form. Doesn't necessarily have to be in primes to be considered factorization. But if it is in primes, then it's called prime factorization. Right? Factorization containing only prime numbers. Okay, so let's go and put in just a few examples of things. Can you give me some examples of prime numbers? 7, because it's 7 and 1, right? What else? 3. Can somebody give me a larger one? Some fun larger one, you know? 17. Make it too big, and then we're going to have to figure it out. I'll do one that I had an example that came across my path the other day with my daughter at home. 43 is one, so a little bit larger. It's prime.
47.
I think 47 will work too. Yeah, lots and lots of prime numbers, right? Yeah, lots of prime numbers. All right, some examples of composite numbers. I already gave you one, 6. What else? 2 is prime.
Oh, just kidding.
In fact, it would be good for us to list 2 because it's a very unique prime number. Why do you think that I think that it is unique?
The 1 and 2 are right.
Nope, but that's a good guess. It's what? Somebody said it. What'd you say? It's the only even. Yeah, it's the only even prime number. All the other prime numbers are odd because even numbers bigger than 2 divide by 2. Yeah, okay. So 6. What else do we have for some composite numbers? 8. 10. Give me a big one. 9 works. A big one? Don't tell me so big that I can't know, huh? 42. All right. All right, we'll stop. Okay. Can you guys think of a number that I can't put in either list?
1. Negative 1.
Okay, so we're only working with positives. Good guess. Good try. No negatives here. We're not talking negative numbers. Somebody said the number 1, and that's the number I was thinking of. The number 0 is a tricky one, and we're really not talking about the whole numbers in the sense of factoring because 0 can't be a factor anyway. It just doesn't make sense when we're working with it. So we're talking about numbers that are bigger than 1. 1 cannot go in either list. And the reason it can't is because prime numbers have to have how many factors? 2. How many factors does the number 1 have? 1. So we can't put the number 1 in either list. So you can't say that you can always classify numbers as prime or composite. You can if you say they're bigger than 2 or 2 are bigger, but you can't classify the number 1 in either category. It's kind of a funny one. Factorization first. I mentioned this a moment ago. If you had a number, say like the number 12, then 4 times 3 would be considered a factorization for the number 12. It is. But it isn't a prime factorization. A prime factorization will still use the number 12. Would be something like this, 2 times 2 times 3. Right? Or if you prefer, you can write it with powers. It's 2 squared times 3. Here's a fun fact. We'll encounter it later in a more concrete form, but there is one and only one prime factorization for every number. You can always break it down into the exact same primes. So that's really good for me when I grade papers because it means that I don't have to make sure that you have an answer that doesn't match mine and it still works. It's not possible, okay? So what we're going to work on in the rest of this paper is actually how to do prime factorizations with some different contexts, because the three examples, if you look on this page, are all very different. The first one is something that you might see when this is first being looked at in like 4th, 5th grade. Okay? It just says, what's my number? 23,660. Okay, so that's a very basic kind of one. The second one is already in a factorized form. It's just not in prime factors. So occasionally I have somebody who wants to multiply this all out, and I'm like, oh my goodness, no. We don't want to make the problem harder. Don't do that. People will still do it on their tests even because they get stuck and they don't know what else to do, so they'll go the hard way. Can it be done? Yeah. I don't recommend it. All right? And then this one over here is what happens more when you get to middle school. And I'll explain why. You don't always necessarily see it with numbers specifically, but you see it with variables, with factoring, with components of things that are being added. So all of these are 3 very different problems. So let's take a look at the most basic one first. And I'm going to show you 2 different algorithms or strategies or ways of factoring. You may be familiar with both of them, or you may be familiar with one or the other and not. So the first one that usually people are most familiar with are factor trees. So a factor tree has this really nice feature of being very flexible. So I can look at this and I can start the factor tree differently than Katie starts it differently, than Jackie starts it different than Dylan started it. We can all end up with the same answer. So that sense of flexibility is really nice. But it also has a sense of disorganization that can sometimes lead to problems. So let's take a look, and we will do this problem together so that we make sure our factor trees look alike, just so that we have the same view at the end. So somebody tell me a number that when you're looking at this that you could divide this by. Bigger is better usually. 10's a really nice one because it ends in 10, right, Katie? Yeah. So if I divide this by 10, what is the other factor? What do I have to multiply 10 by to get 23,660? Okay. 10. We'll start with the 10. Is 10 prime? No, so we keep going. How will 10 factor? 2 and 5. Once I get to primes, which 2 and 5 are, I'm done with the branch of that tree. So let's come over here now to 2366. What does this number divide by? Don't go straight in your, just tell me one. 2. Yeah, that's what I would say if I looked at it too, because it's a big enough number that I'm not familiar with all of it, right? So if you divide this number by 2, what do you have? 1183. 1183. Still a pretty large number. I know it doesn't divide by 2. How about 3? Nope. How about 5? Nope. How about 7? Maybe. We don't have a factor tree. We don't have a divisibility rule for that one. So check it out for us, Catalina. Does it divide by 7? It does. And if you divide it by 7, what do you get? 169, which might be a number that you're familiar with. It has a factorization as well. Does anybody remember what its factorization is? Okay, if you don't, let's go through it again. So 169 divisible by 2? No. 3? What did you say, Colton?
13.
It's 13, yeah.
513.
It's 13 squared. That's why sometimes people are familiar with it, is that somewhere along the way, about half of the teachers you've had probably forced you to memorize some powers of 2, oftentimes up to 15 for whatever reason. I don't know why 15 is special and you stop there, but a lot of people know they're up to 15 in the back of their mind somewhere. Okay, if you didn't, you just keep going up the ladder, all right? So we divide by 2, doesn't work. Does it divide by 3? No. Does it divide by 5? No. Does it divide by 7? No. We just try primes all the way along. Eventually you'll hit 13, it'll work. All right, so in this, depending on how neat and tidy you work, will depend on whether or not it's easy to find or maybe easy to lose, different factors in your factor tree. So in my factor tree, I've got 2 and 5, and here's this 2. Here's a 7 and a 13 and a 13. And you have all of them as well. Maybe easy to find, maybe not. And these are the factors. So when we write down our answer, we would say that 23,660 is equal to 2. How many 2's do I have? 2, so that's 2 squared. typically write the next smallest number next. What would you write next? 5. How many 5s do you have? Just one, so we'll just write 5. What's next? 7. And how many are those? One of those. And then we'd have 13, and we have 2 of those, so it'd be 13 squared. Factor trees are fine. Totally cool. If you like factor trees, use factor trees. I do want to show you one other way to do it. I don't remember when I was introduced to this, but it was, I feel like that it was in middle school somewhere, and I thought, oh, I really, really like this. So this is 23,660. And do you remember how we did that top hat, it looked like a top hat division thing where I went like this in the last, you remember that? Okay, so this kind of feels a little bit like that. I'm going to divide, but I want to start with the smallest prime number that divides this. So what is the smallest prime number that divides 23,660? 2. And I would divide it. So I'd have 1, 1, 8, 4, 0. 8, 3, 0. Sorry, there we go. And then we do it again. What's the smallest prime number that divides 11,830? Another 2. And if I divide another 2, I get 5,915. Okay, just 2 divide this. No, just 3 divide this. No, but 5 will. So 5 is my next one. So if I divide by 5, I actually get the 1183 that we saw pop up in the other one before. I already know that 2 doesn't work and 3 doesn't work, and I can see right now that 5 doesn't work, so I don't have to keep looking at those numbers. I've already divided them as many times as they will. So 7 would be my next possibility to test, and that's kind of a nice feature, is that I'm working my way out of prime possibilities as I work my way up or down this ladder. So what is 1183 divided by 7? 169, which we know because we saw it before, and then we get the 13 and the 13. Kind of the nice thing about this is the nice thing that happens in like lattice multiplication or in the division algorithm that looks like the top hat, is that the answer's all right here. Right? So I don't have to go searching for all the pieces. They're all there, and they're all in order even. Right? I see the 2's beside each other, so it's 2 squared. And then there's a 5, and then there's a 7, and then there's a 13 squared. And so my result is all in sort of a neat, orderly form. Your call. I don't care which one you use. I won't even ask you to use a specific one. This isn't one of those kind of things. I just want you to know that there's more than one way to do it. All right, any question on either of those methods? Yes, Colton.
Never mind.
Okay.
That's my question.
All right, let's take a look at part B, because part B is one where I said that it's already in factored form, just not prime factored form, right? Okay, so this one is kind of like the one that you guys asked me about on the board here that had the 10 to the 4th and the 6 to the 4th in it, and I said, well, basically we can use some properties of exponents to make our lives a little bit easier and to factor this a little further, and we can do the same thing on this problem. So as you're taking a look at the number 16, how does the number 16 factor? Just the 16. In fact, I don't even want to write it right there. I want to write it sort of separately as a observation. How does 16 factor?
4 and 4.
4 and 4. And then 2, 2, 2, lots of 2's, right? So if I'm rewriting this, which I will next, the 16 can be replaced by 2 to the 4th, which still has a 4 on it from here. Okay, so all I did is the 16 itself is replaced by the 2 to the 4th. Then we're going to do the same thing with 81. How will 81 factor?
9 and 9.
9 and 9,
Bunch of 3.
and then a bunch of 3's. Yep. In fact, there happen to be, in this case, again, 4 of them. So I have 3 to the 4th, and then I have that same 4th that was already there after that. And then I have a 6. How does 6 factor? 2 and 3. So that's 2 times 3 to the 6th. Okay, everybody good so far? Yeah? All right, cool. This is properties of exponents. That's what this is boiled down into at this point. So when I have a 2 to the 4th raised to the 4, how does that simplify? Yeah, I multiply them, right? That's 2 to the 16th. And when I have a 3 to the 4th raised to the 4th, how does that simplify? 3 to the 16th. I multiply. Now, I don't have the same thing happening here at the end. I have 2 times 3 to the 6th. How can that be rewritten? I can write 2 to the 6th, and I can write 3 to the 6th. And Michaela wants me to do something else with them after that. She's just jumping the gun. But this one first, right? Okay, everybody good with that step? Yeah, so I distribute the 6 across. That's the way that works because it's multiplication. 2 times 3 to the 6th. And then, yes, I can combine the ones that have the same base. I have 2 to the 16th, and I have 2 to the 6th. So what is 2 to the 16th times 2 to the 6th? Yeah, and how did you get that, Catalina? Right, we add the exponents together. Yeah, all this is hinging on what we did back in chapter 3. So this is 2 to the 22nd. And then I have 3 to the 16th and 3 to the 6th. So that will happen to be also 3 to the 22nd. Okay? This is a huge number. If you try to multiply this out instead of factor what you start with, it's going to be a mess. I don't even know if it's small enough that your calculator can tolerate it. I think it's probably not. Yeah, it's not going to work. Okay. Next problem is an interesting one. So like I said, this is definitely more like middle school kind of question. But what I want you to recognize is because of the addition in it, we're actually able to do some similar things to what we would do with an algebra question, like when you work with x's and variables and things like that. So what I'd like for you to do is I'd like for you to take a look at the 2 sets that are separated with addition and first pick out what do they have in common. So let's start at the beginning. The very beginning of the first one has a 2 in it. Do both of them have a 2 in it? Yes. The first one has 2 2s, and the second one has 4 2s. Is everybody good with that? So if this one has 2 and this one has 4, how many do they have in common? 2. So I'm going to first write that down. That what they have in common is 2 squared. We're going to go down the line and we're going to do the same thing now with the 3s. So 3s. Both of them have some 3s in them. The first one has 5. The second one has 4. How many do they have in common? 4. They both have 4. So this will actually be 3 to the 4th. And then I'm going to take a look at the end. I have 7 to the 55 in both pieces. So they both have a 7 in them. How many 7s do they have in common? 55. So this one at the end is 7 to the 55. Now I'm not done, but does everybody understand what I've done so far? I've identified the pieces they have in common. And what I've done is I've taken them and I've pulled them out. I've extracted them from where they were before. It's called factoring. I mean, that's what we really did. And when we do it, we're still left with other things with an addition sign between them. Okay? When you pull something out, what you're doing is you're dividing it. So you're always going to be left with something on either side of the addition sign. It could be a 1. You could be left with a number 1, like right here. We don't on this problem, but you could be. Because division never ends in 0. I never divide 2 numbers and get 0, right? Not unless one of them was 0 to begin with. If I'm dividing something that has value to start with, it will still have a value at the end. So what we're going to do is we're going to go back up and erase all my marks. And we're going to take the pieces one at a time again. Looking at the first set of factorizations, I had 2 squared. And I pulled out 2 squared. So are there any more 2's left? The 2 squareds got pulled out completely, right? So there's no more 2 squareds left. I had 3 to the 5th right here, and I pulled out a 3 to the 4th. How many 3's are left? 1. So right now, I do still have something here. So you could actually say when I divided this, 2 to the 4th divided by 2 to the 4th is 1. But 3 to the 5th, I'm left with a 3, and I'm left with 1 3. And so I pulled out that. I'm left with a 3. So I was left with a 1 here and a 3 here. 7 to the 55. also pulled it back out, so I'm left with a 1 here. So really, I'm left with 1 times 3 times 1. I think I like writing it up there. I think I'll do that above it. And that's a 3. 1 times 3 times 1 is 3. Now we're going to do the same thing over here. I have 2 to the 4th, and I pulled out 2 squared. So how many 2's am I left with? I'm left with 2. So I'm left with here 2 squared. I had 3 to the 4th, and I pulled out 3 to the 4th. What am I left with? No, well, I'm left with 1, right? Because it's division. Pulling things out is dividing. 3 to the 4th divided by 3 to the 4th is 1. Okay. How about the 7 to the 55? Also happens to be a 1. So 2 squared times 1 is what? It's 4. So on the other side of the addition sign, I happen to be left with a 4. This is not finished, right? Because what can you still do? I can add 3 and 4, you betcha. So right now, again, I still have 2 squared, 3 to the 4th, 7 to 55, and now I have 7. Am I finished? So close. Yeah, both of these are 7s, right? So this one is an understood 7 to the 1. So I'll combine things when I can. I have 2 squared, 3 to the 4th, and then I have 7 to the 56. Add exponents. One thing I want to just sort of say out loud so that nobody's like worried about it later. You'll notice like on C, I put dots between my values, and on B, I didn't. As long as they've actually got powers next to them, it's an understood multiplication when they're side by side. But if you had, say for instance, like over here on the first problem where it was 2 squared times 5 times 7 times 13 squared, and the 5 and the 7 were beside each other without the dot, we would look a lot like the number 57. Do you see the difference? So it's up to you whether you put them when you don't have to or not, but if you just want to be extra clear and put them all the time, that's certainly fine too. Any questions on either, especially these last 2 processes, because they are a little different? Okay, we're stopping there today, guys. Have a great weekend.